Hello, my dear students. Now, this is part number 2 with lecture number 5, dealing with the metal oxide semiconductor field effect transistor. Let me first, as usual, start with a very quick flashback on the content that has been delivered with the first part of this lecture, and then let's go with the second part. Okay, as I mentioned earlier in the first part, this is one of the very important lectures, as this MOSFET is considered as the main building block for every and each analog and digital electronic device nowadays. That's why this will be somehow majorly reflected in your final or unseen exam with one complete question with about 3 marks. And also it has this very important effect with your coming courses, starting from electronics 1 and so on. So let's first start with reviewing what we have already learned in the first part. So in the first part, we first introduce the schematic of the MOSFET, or the metal oxide semiconductor field effect transistor, as it consists of a source, a drain, both are N-type, and then we have a substrate which is P-type. By the way, we call this MOSFET as an N-channel MOSFET because in the beginning of the next of this part, we will study quickly the other perspective or the other type or the second type of the MOSFET, which is the P-channel MOSFET. Then we have here a source, a drain, both are N-type with a substrate B-type. We have an oxide layer, which is an insulator layer, and then we have metals indicating the electrodes. We have one electrode on the source, we have one electrode on the drain, we have one electrode on the body, and we have an electrode on the gate. So we have source, drain, gate, and body. During our module, we will usually consider this body is connected to the ground, so it is basically inactive terminal. So we will keep these 3 terminals: the source, the body, the source, the gate, and the drain are at the 3 main terminals in our device. First, we start by investigating the energy band diagram, but please take care that we consider now this energy band diagram. Please monitor my pointer. So it's this cross section, which is the NPN cross section. So that's why we plot this energy band diagram, illustrating the NPN configuration. Here, the majority carrier is the electron. It's the same with the right-hand side. And in between, we have holes as a majority carriers. Electrons in both sides will not be able to move to the other side because of this barrier. And also the holes in this intermediate region, which is the gate region, is also bounded due to this well or double barrier in the left and the right. So this is the configuration. Now our target is to convert this device to a position where majority carrier can be able to move. So this position is under what's called the thermodynamic equilibrium position because we have a flat Fermi level. Now we are going to be far from the thermodynamic equilibrium, and we are going to force the electrons to move from the source to the drain, or in the other word, we are going to get rid from this barrier. So in order to do so, we have to do actually 2 steps. The first step is to put a positive voltage on the gate. So whenever you put a positive voltage in the gate, then holes in this region will going to repel because the holes have also a positive charge. And this region is first converted to an intrinsic region where there is no electrons and holes. After that, we have electrons that can be attracted here and confirming or implementing what's called a channel. This channel is an N region area connecting the source to the drain. So we call it this channel because it's simply a channel or bridge the source to the drain. And now we have a link between the source and the drain with an N region channel. In order to create this N region channel, you have to insert some positive voltage in the gate. The value of this positive voltage is called the threshold voltage. So again, the threshold voltage definition is the minimum amount on the gate that can create an N region linking the source to the drain. So as a next step, now you have the channel, you have the bridge between the source and the drain. However, electrons will not move from the source to the drain simply because there is no reason to move. This source is grounded and this drain also is grounded. So basically no reason for the electron to move from the source to the drain or vice versa. So the second step is simply to put a positive charge on the drain. Now, electrons in the source will start to move to the drain because simply there is here a positive charge and electron is a negative charge, and the electron will start to move from the positive to the negative. As far as you increase this positive charge, more electrons will gonna to move from the positive region to the, or sorry, from the source region to the drain region. So in this case, the voltage and the current are directly proportional. Whenever you increase the voltage, you increase linearly the current. Then, what if you increase more and more the VDS or the volt applied to the drain? Remember that we are using here the term VDS because simply the source is grounded, and here we can use the term VGS again for the same reason because the source is grounded. So what if you increase this positive voltage more and more? Then we found that this channel will start to have this sloped performance. Why these slopes appear? Simply because the probability to find an electron here is smaller than the probability to find an electron there. Whenever there is an electron here, this electron will be automatically attracted to the positive charge because the distance between the electron and the positive charge is larger. However, the probability to be attracted here is less. So the probability to find an electron here is more. That's why we have this slope structure, which is proportional to the positive charge applied to the drain. Whenever you increase this positive charge more and more, you reach this point where the width of the drain stands to 0. This point we call it the pinch-off point. Again, the pinch-off point is the value of the drain voltage that makes the channel just behind the drain is equals to 0. This value typically or mathematically equals to VGF minus V threshold. So whenever you have a VDS or voltage applied to the drain equals to VGF minus V threshold, pinch-off starts to appear. Whenever you increase this voltage, then the pinch-off point starts to go toward left. And this region becomes what's called a depleted region because in this region you don't have an electrons and you don't have an holes. You don't have an electron simply because any electron will be directly attracted to the source. Sorry, to the drain. It will be directly attracted to the right-hand side. And of course, you don't have holes because simply you have a very high positive charge, so any hole will be automatically repelled. So this region becomes a depleted region. That's why it has a very high resistance, which is typically infinity. Accordingly, this is a complete scenario from first exciting the gate with a positive voltage to create the channel. Then this channel starts to increase. After that, we have this slope due to the high VDS. Finally, we have the pinch-off that can be moved toward the left side whenever the VDS is greater than VGF minus V threshold. Finally, we have this IV characteristic curve, which include actually 3 regions of operation. The first region here, which is actually corresponds to this region and this region, actually to this region exactly, when the voltage and the current are directly proportional. So this, so this is the linear region, or what's called the triad region. In this linear region or triad region, as you can see, the voltage is directly proportional or linearly proportional to the current. So by increasing the VDS or the voltage applied to the drain, the current flowing from the drain to the source, or simply the electron flowing from the source to the drain, is linearly proportional. After that, whenever you reach the bench-off point, when VDS is equal to VGS minus V threshold, then the current starts to saturate. And here you have this infinite resistance, because please remember that the resistance in this curve is 1 over the slope. So as you can see, this slope is 0, though the resistance is infinity. So this is simply the IV curve. We have the triad region, and we have the saturation region, and the clear cut between this triad region and this saturation region is simply the point at which the pinch-off occurs, which is VGF minus V threshold. Now, we have a third region of operation, which is the cutoff region. The cutoff region is the region at which the VGS is smaller than V threshold, which is this region. In this case, no channel is created, and simply you don't have current. So that's why this is directly overlapped over the x-axis, because you don't have current. practically speaking, in the saturation region, we don't have an infinite resistance. However, we have a finite resistance with a very high value. So practically speaking, this IV curve tends to be, looks like that in the saturation region whenever we have a practical MOSFET. Now, this is what we already have done in the first part of this lecture. In the second part of this lecture, we are going to discuss actually two main points. The first is the another, or what we can call the complementary of the N MOSFET, what's called the P MOSFET. So the N MOSFET or the N channel MOSFET is this MOSFET where we have an N channel linking between the source and drain. So basically, the source and drain are both N, and you need to create an N channel here in order to link the source with the drain. So we put on the gate a positive charge. What about the other complementary scenario? Whenever you have the N well or the N substrate and the P are the source and the drain. So let's now together start to explore the other complementary of this MOSFET, which is the P channel MOSFET. So let's start first with investigating the structure of this MOSFET. So simply speaking, we have now an N substrate. And inside this N substrate, we have two doping wells, both are P plus, to indicate both the source and the drain. Similarly, or similar to the N channel MOSFET, we have an oxide layer here, where we have the VG or the gate terminal. So again, we have the source, the drain, the gate. Of course, we have the body still. But, oh, so I'm sorry, this is the body. But the main difference here between the source and the drain, or the main difference actually between the N channel MOSFET and the P channel MOSFET is that now the substrate is N and the source and drain both are P time. Okay, so let's start to repeat the same story. The first step is that you would like to make some sort of linking between the source and the drain. Now the source and drain both are P time. So the linking should be also a P time. So you need to convert this region or to invert this region to be a P time. So in order to invert this region to be a P type, now you need to add a negative voltage on the gate. Because this negative voltage on the gate will first repel electrons, which is the majority in the substrate, and then attract holes and then create this channel that's bridge between the source and the drain. So this is the first difference in the operation. In the N channel MOSFET, in the N channel MOSFET, you need a positive gate voltage in order to create the channel. In the P channel MOSFET, you need a negative. So that's why this is called the P channel. In the P channel MOSFET, you need a negative voltage in order to create the channel. So you have to expect that your V threshold here will be a negative voltage. And you have to expect that you need a VGS, which is smaller than V threshold, in order to operate, because these numbers are in negative. So for example, if your V threshold is -1 voltage, then you should expect that your VGS should be -1, -2, -3, or something like that, in order to make your MOSFET operate. So this is the first difference. Okay, what is the second? Or sometimes, just to make sure you understand it well, sometimes we write it here a VSG, but I would prefer to make it VGS, just to keep sign. So this is a negative, and this is a negative, and you compare two negative values to each other. So I prefer to write it like that. Okay, so this is the first step. Now you create this channel, but again, nothing will push holes to go from the source to the drain. So in order to push holes to go from the source to the drain, now you need to add here a negative voltage again. Now, holes here will be attracted to the negative voltage and will move in this way. So the second issue is that your VDS now also is negative. So you have a negative VDS. And holes are moving from the source side to the drain side. Again, please remember, my dear students, that terms still have the same definition. So again, the source is the place where you stock your carriers, which is hole. And the drain is the place where your carrier journey is terminated. So that's why it's called the drain, and that's why it's called source. In the N-channel MOSFET, your journey is due to electron. Now your journey is due to holes, but with the same way or the same concept. Also, please don't forget the word unipolar and bipolar device. This MOSFET is a unipolar device because current is only due to either electron in the N-channel MOSFET or holes in the P-channel MOSFET. However, in the next lecture, inshallah, we are going to demonstrate another type of a transistor, which is called a bipolar junction transistor, where the carrier or the current is due to both carriers, electrons and holes. We already have studied this while we are dealing with the p-n junction in the previous lecture. The current were due to, the current was actually due to both electrons and holes. So this is a major difference. Okay, so as you can see, now we have a VDS negative, now you have a VGS negative, the same theory. However, now the carriers are holes, not electrons. So this is very important to understand. And by the way, during your tutorial session, you will gonna solve a lot of problems either using the M-channel MOSFET or using the P-channel MOSFET in order to explore actually different of operation. Actually or conceptually, both are working with the same concept. However, it's only a sign matter from a VGS positive and VGS positive to a VGS negative and VGS. So this is what you should do. You can make some home exercise by plotting the energy band diagrams of this structure and also plotting the IV curves of this structure. It will be something very interesting, but actually it's something easy, by the way. There's only one small tip or advice. Now, hole is moving from the source to the drain. So you have the current here moving from the source to the drain. So if I produce ID, which is the current in the drain, in the P-channel MOSFET, this ID will be negative because the definition of the ID is the current flowing from the drain to the source. So if you are considering ID as a current flowing from the drain to the source, this is negative because now current is flowing from the source to the drain. However, in the N-channel MOSFET, your electron were moving from the source to the drain, so your current is from the drain to the source. So this ID is positive. So this is simply leads that this IV curve can be plotted in the third quadrant because now VDS is negative and ID is negative. Of course, you can simply plot it in the first quadrant if you alternate the terms. So you can say that, okay, this is VSD, so it becomes positive, and this is ISD, so it becomes positive, and then you will have typically the same IV curve that compared to what you see. But in the third quadrant, it will look like that. And so on. At different VGSs, and again, of course, here VGSs also is a negative value. So it is very simple. So this is what we need to know about the P-channel MOSFET. As you can see in my presentation, I will turn back to my presentation in seconds. So as you can see in my presentation here, this schematic or this block diagram shows both N-channel MOSFET here in the left-hand side and B-channel MOSFET on the right-hand side, both in the same wafer, the same substrate, because simply the technology, you are using both of these transistors together. This is what's called the CMOS technology or the complementary metal oxide semiconductor technology. This is the main technology used in implementing all the digital devices, including your processors, your microcontrollers, and all these embedded systems. So that's why we are plotting those together. Another also important note, and based on our first lectures, we already have studied that the electron mobility is higher than the hole mobility. So that you can now easily understand that the N-channel MOSFET is faster than the P-channel MOSFET, because in the N-channel MOSFET this is directly due to, or the current is directly due to electron. However, in the P-channel MOSFET, the current is due to holes. And as you know that electron is faster than holes, then you can imagine, or you can understand that the N-channel MOSFET is faster than the P-channel MOSFET. Okay, that's perfect. So let's turn to the next slide, which is actually the most important part of this lecture. Now we are going to understand, or we are going to deal with another type of energy band diagram. If you remember in the part number 1 in this lecture, we studied some type of an energy band diagram which represent an cross-sectional part of the energy band diagram dealing with this portion, if you remember. So yeah, this black line. So this black line representing an NPN junction. And we already plot this energy band diagram in the first part of this lecture. And we studied this energy band diagram actually under thermodynamic equilibrium and after applying voltage. Now what we are going to do is with that we are going to plot another energy band diagram in this manner. So this is our new cross-sectional area. As you can see here, we have a metal oxide semiconductor interface. Here in the black cross-section, which is a vertical cross-section, we have a pure semiconductor interface between N and PN. However, here we have a metal, an insulator and semiconductor, which is actually the word MOS. The word MOS indicates for a metal oxide semiconductor. That's why we call a MOS capacitor or a MOS interface, because it's a metal oxide semiconductor interface. Maybe we will deal with the word capacitor by the end of this lecture, but for the time being, let's consider it as a metal oxide semiconductor interface. Okay, but in order to start plotting this energy band diagram, we have first to identify two unknowns from our perspective. Actually, we know how to plot an energy band diagram for a semiconductor material. We already have studied this for a long time. We already know how to make an energy band diagram for a metal or for a semiconductor under a p-type or n-type doping, or maybe under applied electrical field, or whatever the condition. But now we have two new types of energy band diagram. We have an energy band diagram actually for a semiconductor, for a metal, and we have an energy band diagram for an oxide. So these are two new parameters from our perspective. So let's see how we are going to plot this energy band diagram. So this is the first energy band diagram. Let's see now. Okay, so this is the first one. Let's start with the left hand side. This is with the right hand side. The right hand side should be familiar from our perspective. So this is now under thermodynamic equilibrium. So as you can see, this blue region, or it's actually more toward the green, this region is a p-type. So as you can see now, we have EF. EF is closer to EV because this is a p-type, and this is EI, or the intrinsic Fermi level, and this is the EC. So this is a very normal energy band diagram with an intrinsic Fermi level in the middle. The Fermi level is now more toward the valency band because this is a p-type, and so on. Okay, but we have actually some new energy levels and some new terminologies or terms. So this is the first new terminology, which is called the phi f. However, I believe that this phi f is somehow known by us. If you remember, let me return back to this page. So if you remember our previous lectures, so this is EC, this is EV, and this is EFI, or the intrinsic Fermi level. Sometimes, or in some books, it is written EI, it's the same meaning, of course. Now the material is a p-type material, so you will have your Fermi level here. This is your Fermi level. If you remember, we have already considered some equations that can calculate this region, which is the distance between the EF and EV, or this region, which is the distance between EFI and EF. So what's called phi F here is already calculated by us. If you remember, we have a relation to say that P, which is the number of holes, equals to Ni e power EFI minus EF over KT. Actually, this term, which is EFI minus EF, is simply this phi F. So this is simply a well-known or a well-known term from our perspective. But we just call this phi F. So this phi F, whenever this phi F is increasing by increasing the doping, whenever the doping, which is Na, because this P is simply Na. So whenever you increase Na, you simply increase the phi F, and vice versa. So this is the first term. However, if we return back to our presentation in a second, you will find another new level and another new parameter. This is a level where we call it V equals 0 level. We will call it now the affinity level. And we have what's called the phi S. So let's introduce this new level, and this is phi S. Okay, so let's stop sharing for a while. So this new level, which is some higher level here, what we can call the V0 level, or the affinity level, is representing the most far level in the material. If you remember the energy band theory, which is maybe lecture number 1 or 2, we studied that we have what's called the valency level, which are the partially filled level, and we have a conduction band. This conduction band is an empty band. It starts with EC, and it ends with a very high level. Typically, we call it infinity. If you remember that integral form of N and P, we make it, especially for N, when we are calculating EC, we say that it's from EC to infinity. But as you know, infinity is some hypothetical value, some ideal value. For any material, there should be a level which represents the last level in the material. And if the energy is higher than that level, then the electron will be kicked outside the material. So this highest energy level is called the affinity level. And the distance between this highest energy level and the Fermi level, we will call it phi S. Actually, we will not have, or will not be considered in our module. We will not consider an equation to express this phi S, sorry. However, you just need to know the definition physically of this phi S as the distance between the affinity level and the Fermi level. Maybe you can ask the question, why are you introducing this affinity level now? We already have studied along the energy band diagram without this affinity level. We only have the EC, EV, and EF and EF. And we hear nothing about this affinity level. Actually, simply, or to answer this question, the answer is very simple. This affinity level doesn't have a very important role while dealing with the semiconductor material. However, whenever you are dealing with the metals, which is the left-hand side of this graph, you need this affinity level. Because if you remember the energy band diagram of a metal, in the energy band diagram of a metal, we say that we don't have a conduction band and a valency band, because simply conduction band and valency band are overlapped. We don't have an energy gap. So in order to define a metal, we will define a metal in terms of two energy levels, the affinity level and the Fermi level. And now the Fermi level is very important. Why? Because this is the sign that this material is under thermodynamic equilibrium. Please remember, if you see this energy band diagram, you will simply see that we have here what's called EFS, and now S stands for semiconductor, and here we have what's called EFM. As far as EFS and EFM are on the same horizontal line, That simply means that the material is under thermodynamic equilibrium. This is the same concept applied for the semiconductor junctions. And in between, we have an oxide layer, which actually has nothing. The energy gap is very large, so we are not interested to the EC and the EV, so we just plot it in a form of a blank area, as you can see here. So now, as you can see, EFS and EFM are horizontally aligned, so this is a sign for a thermodynamic equilibrium. Now, in this case, the affinity level of the semiconductor and the affinity level of the metal are both on the same level, so simply phi s and the phi m are equal. Phi s or phi m we call the work function. The work function is the distance between the affinity level and the Fermi level. So the work function for the semiconductor is simply equal to the work function of the metal. By the way, in some other cases, I believe in one of the tutorial problem, you will tackle a problem where phi s and phi m are not equal. But for this example, to make it simple, we put phi s and phi m are equal. So this is the case for a metal oxide semiconductor junction under thermodynamic equilibrium. Now, what we are going to do is that we are going to repeat the same story, but on this energy band again. So if you remember, the first step in order to turn off this to turn on this MOSFET is to put a positive voltage on the gate. Whenever you put a positive voltage on the gate, that means that the holes in this region, in the channel region, is going to make some sort of repel. Till we have a depleted region or an intrinsic region, that this region will be converted to be an n-type. So let's start this journey together. So the first step now is to put a positive charge on the gate voltage. So whenever we put a positive charge on the gate voltage, here, as you can see, oh, I'm sorry. So we will start with the negative process, which is the unwanted process, which is to put a negative voltage on the gate. I mean that this, of course, will keep the MOSFET off. But let's see what will happen. So when you put a negative positive here, that means that you convert or you turn this region more and more to be p-type, because holes are going to be attracted in this region. So simply this will happen. As you can see, the doping in this P region starts to increase. This is the first time, because now what about the distance between EFS and EV? As you can see, by going toward left, this distance starts to decrease. This means this region is highly doped with respect to this region. This region, my dear students, is simply this region. So now you have more and more P doped. Again, this is not what we need. This is actually the reverse of what we need, but we just study this process. Another very important sign, my dear students, is that in the thermodynamic equilibrium, the EFS and the EFM are aligned together because no applied voltage. But now, the EFM and the EFS are not applied together, are not aligned together. As you can see, we have this shift, and this shift is equal to the voltage applied, this negative voltage applied. So if I plot this energy band diagram here and told you what is the or is this energy band diagram under thermodynamic equilibrium, you will simply say no, because EFS and EFM are not horizontally applied. And the shifting value between EFS and EFM is proportional to the voltage applied, which is this negative voltage. As you can see, and please remember our well-known quote that holes energy increase by going upward, or sorry, holes energy increase by going downward, and electron energy increase by going upward. So as you can see, whenever there is a hole here, this hole will automatically drift and go to this point, because from the hole perspective, this point has a lower potential energy than that, which is the minimum potential theory. That's why we call this process the accumulation process here. Why we call it the accumulation process? Because in this process, holes accumulate on the electrical field region, as you can see. Okay. The second case is whenever you have a positive voltage on the gate. So whenever you have a positive voltage on the gate, then this region will start to be intrinsic and then n-time. That's it. This is the case. So now the Fermi level becomes more and more far with respect to EV, which is actually the reverse of this region, as you can see. Now the bending is in the other direction. In this point, the material is more toward to be intrinsic. But I can ask you a very important question here. Is the applied voltage here is greater or smaller than the threshold voltage? The answer is very easy. If this voltage is greater than or equal to the threshold voltage, then this point should be turned to be an N region. However, this point is still a P time, not an N time. Because if this point is an N time, then the Fermi level should be above the EFI. So simply, this is a positive voltage. However, this voltage is still below the threshold voltage. We call this as a depletion region. Because in this depletion region, you are now repelling holes from the channel. You are getting right from holes, but you still don't have electrons. Now, what if it means something like that? So just monitor this region. So make a difference between here and this. Now, in this case, my dear student, this region, this point, which is representing the channel point, is inverted to be an N times. That's why we call this an inversion region. So in the inversion region, the channel is now inverted from being a p-type channel to be an n-type channel, or from being a p substrate to be an n channel. And that's as you can see here. So by increasing the positive voltage, so in this region, that potential or the voltage applied on the gate is greater than the threshold region, and that's why this turned to be an N side or an N region. Okay, so this is simply the complete story from a thermodynamic equilibrium, which is a p-type substrate, the accumulation region, whenever you add a negative voltage to the gate, the depletion region, you add a positive voltage, but this positive voltage is still below the threshold, and the inversion region, whenever you invert your channel to be an N channel. Now, you can reach this expression to demonstrate the voltage applied here. However, this expression will not be required from your side, actually, so you don't need to memorize it. This is just to express the voltage needed in order to make this region, in order to make it an N channel region, which is simply the threshold voltage. So this phi s represents the threshold voltage. Now let's turn to a very important part, or a final part in this lecture, dealing with the MOSFET capacitor and the MOSFET charge accumulation. Okay. In order to start studying this part, we have first to investigate why we have a capacitance effect in the MOSFET. Please remember, my dear student, what is a capacitor? What is a capacitor? If you remember the last page or the last slide in the p-n junction lecture, we say that simply, whenever we have a conducting medium, a definition of a conducting medium is a medium that has a free carrier. It may be electrons or holes. And then we have any sort of a dielectrical material. So this is a conducting medium, and this is a dielectric or insulated, and then we have another dielectric material, conducting medium. So whenever you have this format, whenever you have this schematic, then you have a capacitor. Okay, that's perfect. So Do we have something like that in our MOSFET? Let's check. Okay, so now if we monitor our MOSFET, we will see that we have a permanent built-in potential in the MOSFET. Why we have a permanent built-in potential? Because we have here an oxide, as you can see, which is similarly equal to this dielectric. If you can see my hand on the top right of the of your video. So this is a dielectric. This is an insulator. Above we have a metal, which is of course a conductor. Below we have a semiconductor, which have some conductive capabilities based on the holes or the electrons. So in all cases, we have here a capacitor. So what is the value of this capacitor? The value of this capacitor is simply depend on the capability of these two conductors. The top conductor is a metal, so it's a very good conductor by default. But what about the bottom one? Okay, so in the first step here, when we add a negative voltage to the gate, then as we have already studied a few seconds ago, maybe a few minutes, that this region becomes more and more p-type. What do we mean by this region become more and more p-type? It simply means that it's more and more conductive because the conductivity increases by increasing the carriers, electrons or holes. So now you increase the conductivity of this portion of the material by putting a negative voltage because you affect more and more holes. So if you go now to the CV curve, now this is the accumulation region. So as you increase the negative voltage applied to the gate, because please remember that this is a VGS. So as you increase the negative voltage of the gate, as you can see here, then the capacitance starts to increase till it reaches a value where this is actually the maximum number of holes that you can reach, and then this saturates. This curve saturates. So this is simply the first portion of the curve, which is representing the accumulation of holes. By the way, you should deeply understand this point. This is actually the threshold, because in this point you turn on the polarity of the doping from an n-type or from p-type to n-type. So this is a p-type region. Includes actually two regions. This is the accumulation region, and this is the depletion region, where you are still a p-type, but you apply a positive voltage on the gate. So this is the depletion region. So now we have the depletion region and we have the accumulation region. What about the third region, which is the inversion region here? So this is the inversion region. Now you have another type of polarity, which is an n-type. So you increase that. Doping, but on the other polarity, which is n. That's why, I'm sorry, yeah, it's going to increase in this manner. And then again, it saturates whenever you reach the maximum number of electrons. This is the maximum that you can get. So now the capacitance starts to increase, as you can see. So this is the second type of the curve, which represents the accumulation region. Okay, so this is the second capacitance curve. Okay, so this is the inversion region. Okay, what about this curve? Actually, this curve is somehow sophisticated. It deals with the case where you have a VDS which is greater than the pinch-off. Because whenever you have a VDS greater than the pinch-off, then simply, if you remember, you have yes, for example, this side. So we have a depleted region here. So that means that the insulating area starts to increase. In order to understand this, I will try to make it in a better manner. So I will try to make it step by step, because this is somehow important, my dear students. So now let's start with the thermodynamic equilibrium case. So you have, this is the source and this is the drain. Actually, they are outside of our interest now. We have oxide layer here, and we have a metal here, and this is a p-type. So your capacitor is simply this region. This is the first conductor, this is the second conductor, and this is the electrical area. So if you remember the equation, the capacitance equal epsilon, which is the permittivity, times the A, which is the area, over D, where D here represents the distance of the electrical material. By the way, we usually call this T oxide, T sub OX. So sometimes you will find that this D is replaced by T oxide, which is simply this. Okay, this is very easy and very simple. Now, what if you put on the gate here some positive voltage? If you remember, the first step is that this positive voltage will repel holes in the P substrate. Then it will turn this region to be a depleted region. Why it's a depleted? Because it repelled holes and it still did not attract electrons. The next step that it will attract electrons and will turn it to an anode. So if you now study this capacitor, you will find that you have, this is your first conductor, and now this is your second conductor. This is still p time, and the effective distance or thickness of the oxide becomes T oxy plus some distance, let's call it x. So you increase D, then the capacitance decrease. Okay, so this is typically here. This is typically here, this area. In this region, you put a positive voltage on the gate. So this positive voltage on the gate starts to repel the holes and turn this region to be depleted. So the oxide thickness or the effective dielectrical thickness increase. Accordingly, the capacitance decrease till we reach this point. Then this region, please monitor my hand, this region, which is the red region, starts to be an N-type. Accordingly, the effective D starts to decrease again and the capacitance starts to increase. Okay, what if we have a bench off? So let's plot. So again, the source of drain. Now we have a positive VD voltage, which is very big, greater than VGS minus D threshold. And here now you have your oxide thickness. And you have here your metal on the gate, which has again a positive voltage. And you have a pinch off. So your channel looks like that. So let's now start to monitor our capacitance. So if you start to monitor your capacitance, this region is an electrical is an insulator. So effectively, whenever you have a pinch-off, your effective D is increased. And again, C equal epsilon times A over D. So when D increased, the capacitance decreased. So in the case of a pinch-off, your capacitance will not going to increase. It will go to decrease again. That's why we have this curve in the electron or in the capacitance curve. So this is a very, very, very important. That's why I insert a very important tag on this slide, because this is a very important slide in our lecture. So the final step, actually, my dear students, in this lecture is to understand what's called the charge accumulation. Okay, so what is the charge accumulation? Very simple. So, sorry. Oh, okay. What is the charge accumulation? So let's now plot again the source, the drain, and here is the oxide, and here is this gate voltage. And let's start to plot a graph representing the charge Q versus the VGS. So whenever you have a negative voltage on the gate, what we call the accumulation region, if you remember, what you are going to have is that you are going to have holes, because you're supposed to hit a negative charge. This negative charge will accumulate or will attract holes. So it's simply very simple graph saying that okay, this is holes. Holes will increase as far as you increase the positive charge. Sorry, the negative charge. Okay. What about the other side? What about the positive side? Whenever you add a positive charge, what will happen? Let's see. So actually you have two regions. The first region is you have holes, sorry, you have electrons, but you still have holes because the VG is still small. So we will plot something like that till we reach the P threshold. So you have some increase in the electrons. Now this blue curve is representing electrons. So you have some increase in the electrons, but the increase in the electrons is very few because you still have holes. Whenever you are above the V threshold, then electrons will increase. So this is the accumulation, this is the depletion, and this is the inversion. So this is the charge accumulation in our MOSFET. Again, we are only interested to plot the charge accumulation in this region, just below the upside, which is the channel region. So this is simply the curve. So let's now return back to here. So again, as you can see, this is typically what I just plot in the paper. This is the whole accumulation, and this is the depletion region, and this is the inversion region, where you have a huge amount of electrons. And now the channel become an n-type channel. So this is the complete story from the energy bandograms, from the energy bandogram perspective. I mean this energy bandogram considering the metal oxide semiconductor, either in the accumulation or in the depletion or in the inversion, where you already have an N channel created. Okay, then we have also the same story from the capacitance perspective. Here is the accumulation, here is the inversion, is the depletion, and here is the inversion. And finally, we have the same story from the charge accumulation perspective, so you can plot the charge everywhere. So these are very, very, very important for your understanding as well as for your unseen examination. Now, this is the termination for, this is the termination for part number, or for part number 2 in lecture number 5, where we have dealt with the metal oxide semiconductor field effect transistor. Believe me, my dear students, this is one of the very important lectures for your career as well as for this course. So try to study it well. In the next lecture, inshallah, we are going to tackle the third device in our module. We start with the PN junction, then we go to the metal oxide semiconductor field effect transistor, and then we are going to go to the bipolar junction transistor. We will consume only one lecture in order to understand the bipolar junction transistor, or the BJT. And finally, we are going to terminate our course with the thin film and the tunneling field effect transistors, the TFTs. So this is the termination for part number 2 in lecture number 5. See you next week, inshallah, with the bipolar junction transistor. Thank you very much.